Hello and welcome back. In this video, we'll be looking at blockchains. Well, first, what is a blockchain? Yeah, you can pause the video and have a think. Try not to Google around. Yeah. Okay, let's go over. Well, blockchain is a new way of thinking how we share information and validate. So it's a distributed ledger technology to connect different untrusted parties over the internet and store data securely from tampering. This means I don't have to have a third trusted party, but rather I have the whole community of untrusted parties, but um, in a way we are establishing some validation which involves everyone. Okay. Also, it involves using chained hash blocks for authenticity. This means, just like the previous video, we're going to use the hash value such that if somebody makes any change in the blockchain, then we're easily able to verify that somebody has modified it. Okay. Blockchain so far has been a core technology for cryptocurrencies like Bitcoin, Ethereum, altcoin, Dogecoin, whatever coin you can think of, due to this distributed properties. Okay, we'll have a look at this more a little bit later. Okay, and blockchain allows different untrusted people to agree on the state of the system. Okay, so if you want to have a look when this problem kind of occurred, you can look up at Byzantine problem. Basically, you have from the same team, you have multiple people, but they don't trust each one, and you're trying to attack the target. But even if one group pulls out, then the mission may become failed. So everybody needs to come to an agreement what they want to do, whether to attack or not. Okay, so that's the popular problem, and blockchain is trying to address that issue where you have a bunch of untrusted people, and to see how we can come to an agreement. Okay, and finally, the history block. For example, of transactions are stored in a distributed storage nodes, and this hence create us a decentralization network. Okay, so let's have a look. Why do we want to use distributed system? Well, you can think about this. When you are using a financial institution like banks, you choose one and then you rely on the service, and in exchange for the service you need to pay the fees, and basically you are relying on them to do the right thing. Okay, but often people can be very protective of themselves. They don't trust others, and this is the same for any entities that providing you with the service. Hence, if we have a distributed system where people don't trust each other but can rely on the outcomes, then this is a better approach. We don't really have to rely on a particular entity, but we can rely on the system to create us where we can trust the results. Okay, so we want to use distributed systems to avoid single point of failures. So for instance, you have your savings with a bank A, and suddenly bank A goes bankrupt, then all your savings gone. Okay, authority power. So if bank A became so large that all other banks disappear, then kind of like a monopoly, then they can start charging you whatever they want, and this can be quite unfair depending on how they do it, right? And finally, the trust issues. Well, the bank can say they are storing your money, but when it comes for you to retrieve it, they may not actually have liquid money for you to take it out. Okay, things like this do happen every now and then, where banks may have assets, but they are not able to provide you what you need to do. Okay, so there can be some trust issues in that sense. So let's have a look at how the blockchains are created. But first, looking at a single entity, the traditional way of doing stuff. So we're going to use the banking example as our blockchain example here. So we have 5 people, and then what the bank do is basically carry out the process of processing. What the banks do here is to process the request. So, for example, David wants to send Chuck $30. Then David has to tell the bank to send Chuck $30, and they will do the checking whether David has enough balance and whether Chuck is a legitimate receiver and so forth, right? And through that, there will be some fees of some sort. Okay. Some people might say, "Oh, my bank transactions doesn't accumulate any fees." It's yes and no, because by leaving your money with the bank, they are using that money to do some other investments and stuff like that. Okay, so essentially you are creating them, giving them the money to do stuff to generate more money for them, not for you. Anyway, that's the traditional way of doing it, but as mentioned before, some of the problems can be happening with a centralized node. So what we want to do is, okay, instead of having a bank in the middle, why don't we just send money directly to one another? Okay, then I don't really have to pay fees or go through service providers or somebody else keeping handling whatever I want to send over. Okay. So in blockchain, everybody keeps the record of transactions. So everybody knows where the money is going, like this. Okay, so everybody will keep the same transactions. And to make this anonymous, sometimes you don't want others to know who's sending what. Usually the sender and the recipient, it uses a wallet address. We might look at it a little bit later. And wallet addresses are typically used only once, so they are generated on demand. So by doing that, you are unable to trace back to who the sender or the recipient they are. Okay, so this also provides the anonymity of transactions. But for sake of explaining concepts, we'll just use their names here. Okay, so since now everybody has the transaction lists, if an error occurs in one record, you can easily check against other records to validate whether it's your record is valid or not. Okay, so this also means if somebody decides to do some malicious stuff, others can easily check whether the record that the malicious user is presenting is true or not by checking with the others. Okay, so that's the basic underlying a scenario using blockchain. So we're going to have a look at the structure of the blockchain now. Okay, so when a transaction happens, everyone in the network records the transaction. Okay, so Bob sent Chuck $10, then everybody else will get to know that transaction and put it into their records. Okay, and each node records a list of transactions. It's called a block. So inside a block, you have a list of transactions that gets recorded. Blocks have a finite size. That means once the block gets filled up, then you move on to the next block. Okay, so the next block is changed from the previous block's hash. So it looks like this. Okay, one block you have up to n transactions. This depends on the size. Okay, and once you filled up the block, you create the hash of block 1. So for example, this can be XXXX. Okay, and this hash of block 1 will be put into block 2, and then you repeat this pattern over and over again. Okay, so later if something goes wrong, you can easily check the previous blocks to see where it actually went wrong. So to calculate the hash value of the block, we use what we call a Merkle tree. Okay, I'm not going to go into details about how to create Merkle tree, but it has a very good property that it's just a tree of hash value where tracing back to the branches is possible. You can think kind of like a binary tree. So Merkle tree allows you to summarize all the transactions with a digital fingerprint, but also quick and simple tests to verify a transaction is included or not. Okay, and also each branch can be downloaded on its own for verification. So going back here, any of the branch can be downloaded and provide integrity and validity of data. Okay, so these are the properties that Merkle tree has, which allows us to validate the transactions in a block fast and easy. Okay, so what do you do if you have an odd number of transactions? Because Merkle tree has to be a balanced tree. Well, basically you repeat the last hash value twice. Okay, so that's a very simple solution done in order one. Okay, so by using a Merkle tree, we can easily create the hash value of the block. Okay. So now back to the block, we now know how to create the hash value. So we create the hash and then we chain it. Okay. So in block 2, there's a block 1's hash. In block 3, there's a block 2's hash, and so forth. Okay. So the simple struct of blockchain is actually quite simple, as you have seen before. Okay. It's just a sequence of hash chained records. Okay. And when a transaction occurs, the transaction is recorded to peer blocks, okay, using the hash chain. So that is, you cannot modify the transaction. So let's have a look at what happens when you try to modify the transaction. So back to our chained blocks. Let's say we altered some record in block 2. Okay, one of the transaction was updated. Okay, so what happens here is that because you altered the record in block 2, its hash value will change now, okay? And therefore, if hash value of block 2 is changed, then it's going to affect block 3 all the way down to the current block that is being validated, okay? So this is a chain reaction that causes the blockchain to become invalidated if somebody tries to alter one of the transactions in previous blocks, okay? Since all nodes have the same blockchain, you can easily find the error or the alteration where it happened. Okay, so hopefully the blockchain technology is quite easy to understand. It's just the blocks that are chained using hash. Okay, one of the widely used application of blockchain is cryptocurrency. Okay, cryptocurrency, for example, as I mentioned before, we'll use like a wallet addresses, which is a one-time address for transactions, like this. It's quite long, so that there can be a lot of combinations. So you can have like a lot of transactions with an arbitrary length of wallets. Okay, and addresses are used only once, as mentioned before, because we want to keep the anonymity of senders and receivers. Okay, due to its properties described previously. Okay. If you're ever wondering who created blockchain to begin with, Satoshi Nakamoto is the named term given to this entity, which we do not know. Okay, so we don't know whether it's a person or a group or whoever, but that was the name mentioned in the Bitcoin paper, which first introduced the use of blockchain, and it's closely tied with cryptocurrency. Anyway, let's have a look at cryptocurrency now. So cryptocurrency is generated through mining. Okay, so you have to do mining to generate cryptocurrency. However, often the cryptocurrency has maximum limit. For example, in blockchain, there will only be 21 million blockchains ever. Okay, you can check out in that link below. Okay, so currently, last time I checked, which was in August 2020, we have about 18.5 million Bitcoins in circulation. So we only have about 3.5 million Bitcoins to mine. Okay, what happens when you finish mining, right? Because cryptocurrency is generated through mining. what happens? Will miners stop mining? That's a lot of people's question, and basically what people suggest to do or are implementing to do is that those miners will no longer be able to mine bitcoins through mining. However, once all the bitcoins are mined, there should be sufficient amount of users using the cryptocurrency, and therefore whenever such transactions occur, you pay a little bit of fee to those miners. Okay? So that was the proposed idea, to have miners keep working to mine. However, you can see that if we lose the miners in cryptocurrency, that means the miners are the ones that are validating the block, the ones that are calculating the hash. Then the blockchain cannot grow, which means you cannot add more transactions. So it's kind of like an ecosystem where you do have to have miners in order for the cryptocurrency to continue having transactions. Anyway, mining is done by validating the block, as mentioned before, by calculating the hash value for the next block. And this one is a little bit difficult. You can adjust the amount of difficulty by adjusting what kind of puzzle we have to solve. So for example, generating hash is easy, but what we want to do here is create a hash value that meets certain criteria. For example, I want a hash value which has 6 zeros at the beginning. Okay, then I need to add some arbitrary value to my original message. Okay, to do that, and this is a brute force kind of a job, so it takes time and computing resources. Okay, that's why you have some competitions between miners. Okay, and in order to earn cryptocurrency through mining, you have to be the first one to mine the block as well as part of the longest link. Okay, so I will show you what it means. So first, using blockchain for cryptocurrency has some important issues that needs to be managed. Why is there an S there? Anyway, basically things can go wrong, right? So you probably have guessed, people can try to spend twice. Okay, so Chuck sends Bob money, but Chuck can also send Alice money, but Chuck doesn't have enough money to do that. Okay, that's called a double spending attack. Also, there's a majority malicious nodes, which means you can dictate how the information stored in blockchain can be altered. This means if I own the majority of the computing resources, then I can do things like double spend attack and say that it's legitimate. Okay. So all of this is arising from this consensus problem, where people can agree or not. Okay. So consensus problem, people are still trying to develop some very efficient algorithms to solve this. So you can be the one too. So basically it's like this. Eve tries to send Bob and Alice $10 each. However, what Eve has is only $10, which means we should not allow Eve to spend more than $10, which means one of the transactions should not be valid. Okay. So when a transaction happens, all nodes will vote which one it will try to keep record of. Okay, the transaction that has the majority of votes will be recorded in the blockchain, and this is based on what the transaction record that each node is keeping. Okay, so it's kind of like this. We're going to do the vote for the transaction. Basically, what it's saying is David has voted for Alice. Maybe that transaction came in first. Okay, it's going to record it, and so forth. Okay, so whoever has the majority vote, that transaction will be recorded. The other one eventually will get discarded. Okay, so out of these two transactions, only one will be kept in the longest running blockchain. Okay, this way we can avoid Eve spending twice, and one of the transactions will not become validated. Okay, but the problem is, what if the voters were a bunch of Eves? Okay, So this is where we have the majority of resources owned by the attacker, okay? And we cannot trust every node in the network, like in this scenario. And this is what we call a civil attack. So to overcome this problem, evidence is provided to cast a vote, okay? When you're voting, you need to provide evidence. So this is called proof of work, okay? And this is what the miners do. When you're voting, you are doing the mining. So each node will perform some brute force task, which spends resources, okay? Well, in this context, what is a brute force task? Well, it is like mentioned before, trying to achieve certain conditions of the hash values. For example, the first 6 bytes should be 0, okay? So let's have a look at an example, okay? Given a hash function f, which is like that, given message m equals 29, find the nonce value c such that fm is a single digit. Okay, you can pause the video here and try to crack it. Okay, assuming you have done so, you had to brute force this because there's no pattern in what the output of hash function will normally give. So if you try from 1, you will reach to c equals 13, that will generate a single value. So c equals 13, this is proof of work, okay? By showing this value, you are able to generate some hash value that meets the condition. That's the proof of work, okay? So going back to this scenario where Eve has compromised, well, faking its own identity to be somebody else in the network, okay? But in this instance, Eve only has one computer to perform 3 brute force tasks in order to vote, okay? So Eve has to compute the vote for the Alice. No, Eve has to vote using its own node, but also has to vote using the other 2 nodes that Eve owns. But if you only have a single computer, then this is going to take 3 times longer to do the brute force task. Okay, so eventually some of the transactions will not get the vote and have a different vote. So it's kind of like this. So we have existing transactions, and suddenly 2 transactions has occurred. Okay, then we have to follow one or the other. Okay, and this scenario is called fork. And obviously one transaction cannot be kept, and therefore the other transaction that receives the most vote will continue with other transactions. If transaction B was a legitimate transaction, then it will be appended into the longest chain eventually. Okay. However, the one that was discarded at the time will no longer be mined further on. This transaction still remains in the block. However, nobody is going to extend that transaction any further. Okay. So to break that attack, all Eve has to do is come up with more computing power. Okay. However, you can easily see that as the network gets larger and larger, even in thousands of nodes, having over 51% of the computing power can become quite costly and probably not worth the time and efforts to do this. Okay, but still, a blockchain will be susceptible to attacks if an adversary can own more than 50% of the network nodes. Okay. And in addition to that, there are a few other issues that we need to be wary about. For example, forks that can be caused by civil nodes or self-mining. So somebody is just keep mining itself and it's going to create a longest chain. And since there's a tendency of following the longest chain, if you can do this fast, then that one can be used instead of the other legitimate chains. Okay. Selfish mining miners are trying to increase their rewards by keeping blocks private. So you keep the blocks private, make it long, and then this transactions becomes the legitimate one in that network. DNS attacks, you can send peers the wrong information. So that means in the network of blockchains, you may not be able to be routed to retrieve the information necessary from other peers. mempool attacks, flooding new blocks with transactions. You can also carry out DOS attacks. Yeah, and then the list goes on. Okay, so although the idea of blockchain is very interesting and has a good applications to it, there are a lot of different attacks that we still need to consider before setting it up to use it widely. Okay, those attacks have been considered in current viable solutions like Bitcoins, Ethereums, to a certain degree. However, you can always find some other vulnerabilities in these lines of attacks and launch them against that. Actually, the theft of wallets is probably one of the easiest one people do, because a lot of people use Bitcoins through an exchange. So having an exchange for Bitcoin trading kind of defeats the purpose of this the distributed system. However, basically they keep the list of wallets for the customers, and those are easily compromised by attackers. That's why you lose them as well. And often, even if you own your own Bitcoin without exchanges, people forget about the passwords or details to access them. So I believe there is quite a large number of Bitcoins that are no longer accessible because simply people have forgotten it, or people who owned it has passed away without passing on to the passwords. So anyway, there's quite a lot of issues to be solved, but nevertheless, there are always pros and cons to different approaches. Okay, so moving away from cryptocurrency, blockchains can also be used for various other applications, including smart contracts, especially if you are working in the law area, crowdfunding, governance, auditing, file storage, and so forth. Because it provides the trusted outcomes amongst untrusted parties, this can be useful in various applications, as well as providing that no transactions, illegitimate transactions gets recorded. You can easily pick them out if somebody tries to alter the records or something like that. Anyway, that's the end of blockchain video. I'll see you in the next one. Bye.